So let's look at 102p. So this is an improper integral, and there are two types of improper integrals. One type is where we have limits of integration that are infinite, and you can see that is not the case here because we have finite limits from 5 to 6. So the other type is when we have a infinite discontinuity, or basically a vertical asymptote. So on the interval from 5 to 6, will we have a vertical asymptote? Yes. When x is 5, we have a problem, don't we? This expression here, 1 over x minus 5 to the 3/2 power, would be equal to 1 divided by 0, which is undefined. Graphically, we know that's a vertical asymptote. What's happening is x gets closer and closer to 5. In this case, since we're going from 5 to 6, if you want to think about that interval from x equal 5 to x equals 6 along the real number line, we can sketch what this function looks like, over that interval. There's a vertical asymptote here. So as we get close to 5, the function is rapidly increasing towards infinity. But the important thing is, as we approach 5 from the right or positive side, then we're approaching that vertical asymptote. So we need to rewrite the improper integral in a way that allows us to use the fundamental theorem of calculus, part 1, and that will involve, of course, a limit. And in this case, of course, we're taking the limit as t approaches 5 from the positive side. So t is some number between 5 and 6, say like here. And now I can say, okay, this is no vertical asymptote under the curve from t to 6, right? So I can look at this integral from t to 6 of this function. That's a finite quantity. There's no vertical asymptotes. I can use the fundamental theorem of calculus part 1 on that. Of course, I'm going to get an expression in terms of t, all right? And then what? Now we take the limit as t approaches 5 from the positive side. So as t gets closer to 5, does this area under the curve remain finite, or do we become infinite? If it's finite, if we get a finite value for the limit, we say the interval converges. If the limit is infinite, then we say the limit, or that we say the integral diverges. Okay, so two approaches to this problem. One is with substitution. Well, they're both with substitution, really. If u is equal to x minus 5, right, that's the substitution I would use. Du is just dx, but we do need to change the limits. The lower limit is t, so if I plug t in for x, I get u is t minus 5. Upper limit is 6. If I plug in x is 6, I get 6 minus 5 is 1. So my limits in the u world go from t minus 5 to 1, and I have u 1 over u to the 3/2, of course, which is u to the negative 3/2 du. Now we're ready to use the fundamental theorem of calculus part 1, find the antiderivative by the power rule. So we add 1 to negative 3/2. That gives me negative 1/2, and divide by negative 1/2 or multiply by negative 2. So I get that. I'm going to evaluate that at the upper limit of 1 minus the lower limit of 2 minus 5, t minus 5 rather. And I just want to rewrite negative 2u to the negative 1/2 as negative 2 divided by u to the positive 1/2, or square root of u. So now I can evaluate this. Notice the limit is still there. So when I say on a test or in the homework to use the correct limit notation, you should have the limit here until we apply it. And we're not applying it yet. So it's still there. So we're just working on the integral itself. So now I evaluate it at 1, and I get negative 2 divided by square root of 1, of course, will be just negative 2. And then at t minus 5. Be careful here because it's minus and negative, that becomes positive. 2 over the square root of t minus 5. Now we're ready. So this is the evaluation of that area that I shaded in, right? This area up here that I shaded in is given by this function. So if you change t, you can find the value of the areas. T is between 5 and 6, but as t gets closer and closer to 5 from the positive side, right, from the right, so as we approach it from the positive side, from the right, then notice that this expression here, of course, -2 is not changing. This expression is getting closer to something, what, 2 up top, but the bottom is going to 0. 2 divided by 0, that's approaching infinity, right? It's approaching infinity. And notice the square root of t minus 5, with 5 always being, or t always being greater than 5, we're going to always be a positive value, but it's getting smaller and smaller, closer and closer to 0. So 2 divided by smaller and smaller value is going to infinity. And -2 plus, something going to infinity is going to infinity. So we write infinity. This limit is infinite, we say, right? But more importantly, what's that tell us about the original integral? It says that integral diverges. Okay, that integral diverges. If the limit were a finite quantity, then the interval would converge, and the area that we would have would actually be finite. In this case, we get an infinite area. Okay, so that's one way of doing it. Now, another way I thought of, you could also do the substitution right away first, before writing out the limit notation. So if you do it that way, if I let u be x minus 5, du is dx, then my limit's what? 5 minus 5, the lower limit is 0. 6 minus 5, the upper limit is 1. And we get, with that, right, we just get the limit was from 5 to 6. Now it's from 0 to 1. Same thing, right? Du over u to the 3/2. And so now I can rewrite this in limit notation. This is now the limit, notice, as t approaches 0 from the bottom side, from the positive side, from t to 1. Okay. And the antiderivative u to the -3/2, we've already done that above. It's negative, of course, -2 u to the -1/2, or -2 divided by square root of u. And we plug in 1, and -2 divided by 1 is -2, minus a negative, plus 2 divided by the square root of the lower limit t. And as t goes to 0 from the positive side, this expression here again is approaching 2 divided by 0, so it's going to infinity. And again, -2 plus infinity is infinity. So same thing, looks a little bit different, but of course we reach the same conclusion, that the integral diverges. Okay, so real important to note that I do want you to use the correct limit notation each time until you evaluate the limit, of course, and then also make sure you state whether the integral converges or diverges. Okay.